Okay, so for today's topic, we're moving on now from the mixture problems and solving equations, and we're going to talk about ratios. Now, I know ratios are a fairly simple concept, but it's very, very powerful. To me, ratios are probably the single most powerful tool in mathematics. Because even if you don't know a whole lot about what's going on, you don't have the formulas you need or anything like that, in many cases, if you know some initial conditions or you know some current conditions, you can use ratios to figure out some pretty complicated problems from there. So anyway, a ratio is nothing more than a comparison of two numbers. For example, I might look in this class, if I wanted to compare students between, I'm just going to pick two locations. I'll go between Site A and Site B. We have 4 students in Site A and 8 students in Site B. I could write it just like that in a fractional form as 4 to 8. I could write it with a colon like this as 4 to 8. Or another option is to use the word 2, 4 to 8. All of those express ratios. And there are some other lesser accepted forms as well, but those are the 3 main ones. For the most part, I prefer to write it as a fraction, because as a fraction, we can do a lot of things with it that we normally would do with a fraction. For example, I can reduce it by dividing both numbers by 4 to get a 1 to 2 ratio. I could do the same in this form here by dividing. It's just I'm not used to doing that. I can still divide both numbers by the same thing to get 1 to 2. It's just I'm much more used to seeing it done in a fraction. Oh, we might compare, if I look at the tables in my room here. These tables are 72 inches long and 18 inches wide. So if I want to do a length to width ratio, 72 inches over 18 inches, well, the inches cancel out. 72 and 18 can both be divided by 18 to give me a 4 to 1. Now here's one of the spots where this is a ratio is slightly different than a fraction. If this were just a fraction, this would just be 4. But since it's a ratio, we must maintain that comparison between two numbers. Now something else you'll notice here is in both of the examples we've done. Here we compared students to students. Here it was inches to inches. In both of those examples, we were comparing two numbers that had the same units, same labels. And that is an important feature of a ratio, is both numbers must have the same labels or same units. In other words, the same name. If I were to try to compare 2 feet to 18 inches, that is not a valid ratio like that. Now I can change it, I can alter it so that the 2 feet is 24 inches. And now it's a valid ratio because I'm comparing two things with the same labels. Now, of course, as I reduce this, the inches do cancel out, and I can reduce both of those by 6 to give me a 4 to 3 ratio. Here's another spot where it's different from fractions. If that were a fraction, I would reduce that to a mixed number of 1 1/3. As a ratio, I don't want to do that because, again, a ratio compares two numbers, a comparison between the two numbers. It's not truly a fraction. So you'll notice all of these ratios I have written up here have no units in them. The units cancel out because they're the same, just like inches and inches or students and students. Because a ratio by nature does not require any units. For example, if I go back to this length to width ratio up here for the tables, it does not matter whether that is 4 inches compared to 1 inch or 4 feet compared to 1 foot, or even 4 centimeters compared to 1 centimeter. As long as the units on both numbers are the same, for every 4 units of length, I have 1 unit of width. So I guess the question is, what if I'm comparing two numbers that don't have the same units? For example, let's say we go on a road trip and we drive 365 miles in 7 hours. There is no way to convert miles into hours or hours into miles. So we cannot give them the same labels or same names. So this cannot be turned into a ratio. This is what we call a rate. We talk about rates and ratios together because many of the operations we do with them are going to be the same. But there is a big difference. And as that first big difference is what we just mentioned, a rate compares two numbers that have different labels or different units on it. The second big difference is in a ratio, we most often just reduce it as far as we can and we leave it like that. It's okay to have a 3 in the denominator or a 2 in the denominator. A rate is almost always reduced to what we call a unit rate. A unit rate means the denominator is equal to 1. So to do that here, it's 7 hours. We would divide by 7 to turn that into 1 hour. Which means, of course, we have to divide the top by 7 as well. 365 divided by 7 comes out to be what? 52.1428571 approximately miles. Of course, we'd round that off probably after about 1 or 2 decimal places. But there it is. It's reduced to a unit rate. And because of that idea of a unit rate, we often rewrite it so that the fraction notation gets hidden in the units. So we might rewrite that as like 52.14 miles per hour. And we sometimes even take it further. Instead of miles per hour with the fraction notation, we might just say mph. When we see that, we have to be very careful. For example, another rate we might have on that trip, let's say our car gets 28 mpg. What's mpg stand for? Miles per gallon. Perfect. When we see this, we need to think 28 miles per 1 gallon. Because this is the form we need it in to do any calculations with it. We have to have it in that fractional form or rate form like that. Examples of rates while we're on it. A lot of times we have, well, we've already gone over the ones for cars, miles per hour, miles per gallon. One that many of you are familiar with is probably dollars per hour. You might get paid $7 or $8 per hour at your job. Actually, not 7 anymore because that's below minimum wage, but $8 per hour at your job or something like that. That is a rate, dollars per hour. In the medical fields, we might run into 8 milligrams per kilogram. When we see a rate written like that, when we go to calculate with it, we need to remember that it's 8 milligrams over 1 kilogram. Or in a medicine concentration, we might have something listed as 2 milligrams per milliliter. Again, before we can do any calculations with that, that has to be thought of and written as 2 milligrams per 1 milliliter, because that's the form that's going to go into any of our calculations. Some common rates in medical, milliliters per hour is a big one, or even milliliters per minute is also pretty big. We talked about drops. The abbreviation for drops is GTT. Drops per minute is a rate that we're going to talk a lot about. Something called units. You might hear, if you watch a medical show, you might talk about so many units of whole blood or whatever. A unit is a medical measurement term. Units per hour. You might have 8,000 units per hour or whatever that are being given to a patient. Let's look back at the ratios for a minute. Ratios that we're going to look at, ratios are all around us. We'll get back to the medical field in a little bit, but there are a lot of mechanical ratios out there. You have to use your imagination a little bit because I'm going to try to draw some pictures. Okay, so if you use your imagination a bit, you might be able to see that those are gears. Talk about a gear ratio. Gear ratios, pulley ratios kind of work the same way. what you're looking at is the size of one pulley or gear compared to the size of the other. Now in pulleys, you actually have to use the diameter. In gears, however, since they have these teeth, it's easier just to count the teeth. The distance between the teeth is the same, so counting the teeth tells you how big the gear is. So for a gear ratio, it's the number of teeth in the driven gear compared to the number of teeth in the driving gear. So if we look at these, this gear here has 10 teeth and this one has 6. Need to know which one goes where now. Well, let's assume, I'm going to draw a little more picture here. Pretend that looks like a little small electric motor. Now if I were to separate, I know, it's comical. If we were to separate the gears, one of them is going to keep turning and one of them is going to stop. The one that's going to stop, which of course is the 6-tooth gear, that is the driven gear. It is only turning because the other gear is driving it or forcing it to turn. So the 6 teeth goes on top. That's the driven gear. The one that keeps turning is the 10-tooth gear. It is driving the other gear. It's hooked to the power source. So it's a 6 to 10 ratio, or if we reduce it, a 3 to 5 gear ratio. Outside of mechanical ratios, there are financial ratios all over the place. Bless you. If this were an economics class or an investment class, you might look at profit to income ratio or profit to sales ratios, things like that. You would look at cost to earnings ratios and investment. What we're going to look at is something a little more personal. Excuse me. If you were to go to apply for a loan, one of the big things your bank will look at is something called a debt to income ratio. What that debt to income ratio is literally your total monthly debt payments compared to your total monthly income. So let's say you have a job where your income is $3,000 per month, gross income. So a $36,000 a year job. Your debt payments. Let's say you have a house payment that is $700. Now that's just the payment on the mortgage. That's not the taxes or the insurance that would be escrowed into that. So you have a car payment that is $300. And let's say you have credit cards that you make regular $200 monthly payments. So your total debt, adding that all up, is $1,200. So your debt to income ratio, your debt is $1,200 over $3,000 income. The dollars cancel out. Both of these can be divided by, let's see, 200. Giving you 6 over 15. We can actually divide by 3 again. Giving us a 2 to 5 debt to income ratio. What they usually look for, by the way, is less than a 1 to 3. So 2 to 5 is a little bit more than a 1 to 3. So that is not the greatest debt to income ratio. In the medical field, ratios are all over the place. We talked about some of the rates as far as milligrams per kilogram or milligrams per milliliter for medications and dosages. We also have, when we go to constitute a medication, it might say we're going to combine 300 milliliters of saline with 120 milliliters of lidocaine. So our ratio here of serum to saline is going to be 120 milliliters of lidocaine over 300 milliliters of saline. So the milliliters cancel out. Both of these can be divided by 30. Here's 4 to 10. Actually could have been divided by 60. We'll divide by 2 again. Once again, we have a 2 to 5 ratio. Or we might have a medication. We have a serum. So let's take 20 milligrams of serum that we're going to dilute into a total of 80 milligrams of solution. Well, that is 20 milligrams of serum. The serum to total solution is 20 milligrams to 80 milligrams. Once again, the milligrams cancel out. Reduced by 20 gives you a 1:4 ratio. Now, a note I should make on these ratios. Whenever we see a ratio, there are actually multiple ratios there. Let's take a look here at a student ratio. Let's look at my previous class here. On my previous class, I had construction students and I had telecommunication students. And in that class, there were 8 construction students and 10 telecommunication students. I can do a ratio of construction to telecommunication. There were 8 construction, 10 telecommunication. And I can reduce that to a 4:5 ratio. But that's not the only ratio that's here. I could flip that around because there's really no reason why the construction has to be first. I can flip that around to telecommunications to construction, which would be a 10:8 ratio, or reduced to a 5:4. But there's even ratios beyond that. Let's say I really don't care about telecommunications, I just want to learn about construction. I might do a ratio of the construction students to total students. Well, there's still 8 construction students. How many total are there? 8 plus 10 gives me 18. Which will reduce, both divided by 2 again, to a 4:9 ratio. But I also have telecommunications to total. So that would be 10 telecommunications students to 18 total. Dividing by 2 again gives me a 5:9 ratio. Where this really comes into play in the medical fields is something called a dilution. We're going to talk about this a lot more in the next unit. Dilutions are kind of the basis where we kick off our dosage calculation. A 1:6 dilution means that you have 1 part of medication, so 1 part of serum, in 6 parts total solution. So that 1:6 dilution is a 1:6 ratio of serum to total. Now what we usually use to dilute it is saline, or NS. So what if I want the ratio of serum to saline, to NS? Well, there's still only 1 part serum, but how do we find out how many parts saline there are? Can anybody tell me how many parts saline would be in there? Well, if there's 6 total parts and 1 part is serum, the other 5 parts has to be saline. So a 1 part serum to 6 parts total solution gives us 1 part serum to 5 parts saline. And likewise, we could have a saline to total. We now know that there's 5 parts saline out of that 6 parts of total solution. So a 5:6 ratio. Once we have created the ratios, there's things we can do with it. For example, let's say we know that we need that, let's do a 4:7 gear ratio, which means for every 7 teeth on the driving gear, we need 4 teeth on the driven gear. And we happen to have a motor with 35 teeth on the gear that's connected to it. We need to know how many teeth we have to have on the gear that it's meshing with to get the proper gear ratio. Well, to make 2 equal ratios, we use a proportion. And we talked about this a little bit in our percents, and I'm sure you're all familiar with it. Where is the 35 going to go, top or bottom? Well, which one describes the gear attached to the motor? That would be the driving gear, so that's the 7. So 35 goes on bottom with the 7. So now we can cross multiply and divide to find that missing number, which would be 20. So it has to be 20 teeth on that other gear that the motor is meshing with to give us the proper gear ratio. The proper gear ratio is required for a lot of reasons. One, to get the proper speed. Also to get the proper amount of power transferred. We might have a 2 in 5 dilution, and if we have 16 milliliters of serum, wondering how much total solution we can make. Well, that 16 milliliters goes here. Looking for the amount of total solution down here. Now I said we didn't need the units in here, but in this case I'm going to leave them there because that tells me the units down here must also be milliliters. So I'm going to do 5 times 16 divided by 2 is 40 milliliters of total solution. Well, sometimes this whole cross multiply and divide doesn't work out. We can run into proportions where it's just not set up to be nice and neatly done. Now, if you recall, what we're really doing there, let's say we have a 3 to 5 is x over 35. The cross multiply and divide is a shortcut for the actual process of just cross multiplying. Now, cross multiplying is multiplying the diagonals of a proportion. So this would be 5 times x would make 5x. This one would be 3 times 35 makes 105. And we know that those two cross products or diagonal products have to equal each other. So 5x equals 105. And in a case like this, of course, we're just going to divide by 5 to solve to get that x is 21. Where the cross multiply and divide came from is that we saw that, hey, the step to solve this equation was always just to divide by the 5 or divide by whatever this number was. So we just included that as part of one of the steps in the calculation. But we do run into proportions where that doesn't work. For example, one like this. 5x over 19 equals 50 over 95. Here we cannot cross multiply and divide because this isn't x here, it's 5x. We have to solve for x. So here it would be more beneficial to cross multiply and form the equations. 19 times 50 is 950. 5x times 95 is, oh, what is that? Is that 475x, I believe? So now we know 950 equals 475x, and we solve by dividing by 475. So we get 2 equals x. Another proportion we can run into might look like this. X plus 3 over 21 equals 12 over 63. So again, we will cross multiply. 21 times 12 is 252. This one's going to be a little more interesting. X plus 3 times 63. Well, we're going to do it this way. 63 times x plus 3. We're going to have to distribute. 63 times x is 63x. 63 times 3 is 189. So now we know 252 equals 63x plus 189. From there, we'll subtract 189. It's going to give us 63 equals 63x. And that's a pretty simple one to solve. We'll divide by 63 to get that 1 equals x, or x equals 1. In our medical fields, we have a lot of proportions we can solve. If we're doing measurement conversions, we can actually use a proportion for that if we really wanted to. We have something like 1,000 micrograms equals 1 milligram. We can make that into a ratio. 1,000 micrograms, 1 milligram. Let's say we want to do a conversion. We want to convert 2,400 micrograms into milligrams. Well, we can use a proportion. We know 1,000 of micrograms equals 1 milligram. Now, the 2,400 has to go on top because that's where the micrograms are. So 2,400 micrograms is going to equal X milligrams. Now, if you're looking closely at this, you realize that these are not ratios. These are rates. Micrograms to milligrams have different units, so it can't be a ratio. The proportions work equally well with rates. So we cross multiply and divide. 1 times 2,400 divided by 1,000 is 2.4. Hopefully, most of you are familiar enough with the metric system you didn't need to use something like that to make the conversion, but there's an example of it. Or we might have, if you wanted to use other rates, I might look at miles per gallon. Let's say you drive 184 miles on 9 gallons of gas. And you want to know, if you have a 16-gallon tank, how far can you plan on driving? Well, the gallons have to go on bottom because we need the same units. Have to match them up in our proportion. We're going to cross multiply and divide here. 184 times 16 divided by 9. Gives us 327.11 miles that we can travel on a 16-gallon tank. You might have a medication that is listed at the dosage to be delivered is going to be 12 milligrams per kilogram. We saw this rate up before. Now let's use it for something. So let's say we have a patient that comes in that is 80 kilograms. So that means 12 milligrams per kilogram becomes 12 milligrams per 1 kilogram. 80 kilograms going on top or bottom? Goes on bottom, because that's where the other kilograms are. And we shall cross multiply and divide. 12 times 80 divided by 1 is going to give us 960 milligrams of medication to give. We might have 7 parts medication and 20 parts water as a listed constitution of a medication. And let's say that we need a total of 800 milligrams of solution. In other words, 800 milligrams of water. We need to know how much medication to put into that. So this is a 7 to 20. Now this is a ratio because these are parts to parts. The 20 is the total water or total solution, so the 800 goes on bottom. I'll put the milliliters in there so that we know our final amount up here is also milliliters. And we cross multiply and divide. 7 times 800 divided by 20 is 280 milliliters. Well, in the medical field and in pretty much any other field, a big application of ratios is in similar figures. If we have two figures where one is just a reduction or an enlargement of the other. So let me just copy these and bring it over here. There, you can see that triangle is an enlargement of the other triangle. And let's say that this is 12 inches, 16 inches, and 18 inches here. Actually, that's not right. It's 22 inches up there would make more sense. And down here, let's say that this is 18 inches. We'll call this X and Y. These are what we call similar figures. I'm using triangles just because it's simpler for me to draw. But any figure where one is an enlargement or reduction of the other are similar figures. The way we know they're similar is we look at the angles. At least in triangles, we can look at the angles. This angle and this angle are the same. This angle and this angle here are the same. Which means the third angle must be the same between them. So since those two triangles have all three of the same angles, then the sides must be proportional, or they must be similar. To find these missing sides over here, oops, those two are the missing ones, we use the known side, which is 18 inches, and we find out what side from the other figure corresponds to it. Now I drew these in the same orientation, so it's not too tough to find, but normally we'd look at the angles. The 18 here is between this angle and this one. So we go to the other figure and we find those same two angles. The side between it is the 12. So that's telling us is the 12, when we enlarged it, became 18. So that can be my first ratio. 12 became 18. Now it's 12 inches became 18 inches, but that's fine. If I wanted to reduce that by dividing by 6 to get 2 to 3 ratio, I could, but I don't need to. It's just extra steps. So now if I want to find x, x has to go on the bottom of this proportion because it was from the same triangle as the 18 here. What's going to go above it up here? Well, the side that relates to that side in the other triangle is the 16 inches. Again, it's between the same two angles. So it's 16 over x. And now we can cross multiply and divide. 18 times 16 divided by 12 is 24. So x is 24 inches. And we can do the same process for finding y. We still have the 12 to 18. We're still using those two related sides as our base. Y, well, it's also from the same triangle as the 18, so it's still going to go on bottom. The corresponding side from the other triangle is 22. If we cross multiply and divide, 18 times 22 divided by 12 is going to give us 33. So y is 33 inches. So we can compare sides of similar figures. This can actually be used as a pretty powerful tool in other things as well. For example, let's say I'll just make them as rectangles for now, just make it simple. Say I have a 2 by 5 rectangle. Its area, 2 times 5 is going to be 10 units, 10 square units. Let me label this as inches, inches, and this will be square inches. If I double those to make this now 4 inches and 10 inches, the area does not double. The area, 4 by 10, is going to be 40 inches squared. The area was multiplied by 4. What we can look at there is we can look at the ratio of lengths, or the ratio of sides. We're going to call it lengths, because that's really what we're looking at there. The ratio of lengths, and it doesn't matter whether I'm using the length or the width. I'm just looking at the length of any side. We can compare the 2 to the 4. 2 to 4, or a 1 to 2 ratio of lengths from one figure to the next. The ratio of areas was 10 to 40. Again, we can leave off the units because they're going to cancel out, which reduces to a 1 to 4 ratio. There's a very strong relationship between these. If I take my ratio of lengths and I square it, 1/2 squared is 1/4, or 1 to 4. So if I know the ratio of lengths, I can find the missing areas from that. For example, let me do kind of a weird shape here. And I'm going to enlarge it. So let's say in this first figure here, that this side here is 3 inches. And the area of this whole thing is 32 inches squared. Over here, this is enlarged to 9 inches, and I want to find the area of this whole thing. Well, the ratio of lengths is 3 to 9. I'm going to reduce that to 1 to 3. Both those can be reduced by 3. My ratio of areas, I can't just use the areas right now because I don't have the second area. but I can get it from the lengths. If I square that, 1 squared is 1, 3 squared is 9. I find 1/9, which is my ratio of areas. So now I can put in my known area of 32. That's from the smaller figure, so we'll go with the 1. And I can cross multiply and divide. 9 times 32 divided by 1 is 288 square inches. So you can see these ratios, if you know how to apply them and know some of the relationships, can be a very powerful tool. We can do the same thing for volumes, but we're running a little short on time. We only have 5 minutes left here. So this is a little bit beyond what we normally would do in the class anyway. So I'm just going to give you the homework right now. Page 73, 1 through 39, the odds. We'll turn you this on the homework. I believe all 4 schools are not in session for Friday, so I've canceled the session for Friday. So we'll see you all on Monday. You have a great weekend.